Good morning, folks. Here's the challenge problem for us today. We have this steel washer suspended inside of an empty shipping crate from a light string that is attached to the top of the crate. We're told that the crate is sliding down this very long ramp that is inclined at an angle of 37 degrees above the horizontal. The crate has a mass of 180 kilograms, and we are inside with a flashlight so we can see what's going on, and our mass is 55 kilograms. And we're told that as the crate is sliding down the ramp, we find the washer at rest with respect to the crate when the string makes an angle of 68 degrees with the top of the crate. And we need to calculate the coefficient of kinetic friction between the ramp and the crate. So since we have a bit to chew on here, I would recommend starting with a picture so we can get everything in order. And here's what mine looks like. We have just the crate itself here in brown sitting on the ramp. That's it. First thing I'd like to do is label the ramp angle theta here. So whenever we see theta, it's always referencing the angle that's relative to the ramp. Next, let's include the fact that the box is accelerating down the ramp, which I'll call the x direction. And we also have the washer hanging from the string attached to the roof of the crate. And we are inside, so we can see everything that's going on in there. Now, we were told that there was an angle that makes an angle with the roof of the crate that is 68 degrees. And now, if we look at the two angles here that make angles with the roof of the crate, one of them is 90 degrees. So the only other one that could possibly be the 68 has to be this one right there. Now, let's take a look at the other angle within this triangle. Not the right angle, not the 68, but this one right here, the smaller one. I would like to call this the washer internal angle and give it a very specific designation. Let's call it gamma. So we're going to take the entire amount of degrees in a triangle, 180, subtract the right angle here as well as the 68 degrees, and that tells us that gamma is 22. It is not the same as the ramp angle, so don't make that assumption when you're setting things up. One last thing before we move into free body diagrams and summing things up, let's set up some coordinate axes. And before I said I wanted the acceleration direction to be considered the x, so I will set the positive x direction up and to the right, and I will set the positive y direction perpendicular to the ramp, like that. So this will mean the crate is accelerating in the negative x direction. You can set your coordinate axes in a different way if you choose. Just make sure you are consistent as you go along. But this is the way I'm going to do things moving forward. So let's jump into the free body diagram of the washer next. Remember, we're considering just the forces on the washer alone, nothing else. We know that the washer is going to experience the force of its own weight, pulling directly down. And then there's also the force of the tension in the string, which pulls at these, weird angles that we analyzed earlier in the previous slide. Let's actually try to get some of those angles back into this free body diagram by introducing some kind of helpful guidelines like these, so we can more easily label our angles. And this dashed guideline will represent the top of the crate, and this gray dashed guideline near the bottom will represent kind of the base level of the ramp. So that means we can include the ramp angle down here, which allows us, due to the nature of similar triangles and other geometry that we've covered in other problems, to copy paste the angle into the weight vector over here. Let's also include gamma, that washer interior angle that I talked about here, and then the 68 degrees here. And that's it for the angles. Next, let's break these vectors up into their components, because none of them lie along an x or y axis. So we're going to have to do this, unfortunately. Let's start off with the cosine component of the weight of the washer and the sine component of the weight of the washer. Of course, these will be at right angles to one another, so we can include a little symbology for that here. Notice that the weight of the washer is dependent on a trig identity that is dependent on the ramp angle. That is very important to note, because if we move over to what's happening in the tension, and we do the cosine and the sine components of the tension with the same right angle between them here, they are not dependent on the ramp angle. They're dependent on gamma. So this is why we had to be very careful in setting up this approach, because if we mistakenly thought that theta was the same in these two spots and was mirrored across the origin here, we would be in trouble. So that's kind of why we are delicately approaching the situation. One last thing before we move on, let's include a vector that tells whoever's reading our work that the washer is experiencing the same acceleration in the negative x direction as the crate, right? Since it's attached to the crate and it's inside of it. So we'll move all of this stuff over and proceed to sum the forces on the washer. And I'm going to place F equals ma here in the center rather than like I've done before at the top, because we have a few lines of work to get through and I don't want to make it too crowded on the screen. Let's sum the forces in the x direction first. So any forces that point up and to the right are positive, so T sine gamma is positive, and any forces that point down and to the left, like the sine component of the washer, are negative. So that's how I'm getting this piece of the expression. And we have this equal to ma. However, the acceleration is in the negative x direction. So we can't just slap ma on. We have to explicitly say that the acceleration is occurring in the negative direction. So that's why I've put this negative sign here. And in the next line, I'm going to exchange the weight of the washer for mg for the washer, so mass of the washer times g. And then I'm also going to move this negative sign out front. So it looks like we still have ma going on here, but it's just negative ma, because the crate is accelerating down the ramp in the negative x direction. The goal here is to solve for the sine component of the tension, this quantity right here, which is what I'll do in the next line. We were not given the tension, and we were not given the mass of the washer. So we need to start thinking about what kind of a technique we can resort to in order to get rid of some of these quantities, right? Because we can never answer a problem using quantities that we don't know. So since there's nothing else that we can do besides simplifying this a little bit in this direction, let's move to the sum of forces in the y direction. So that would mean anything that points up and to the left, so this way, is a positive in the y direction, and then anything that points down and to the right, so this cosine vector for the weight of the washer, that's negative. And we were told that the washer remains at rest with respect to the crate as the crate is sliding down the ramp. So that's basically a cue that says, hey, your acceleration in the y direction is 0, right? You're only going to be experiencing, as a washer hanging on a string, acceleration down the ramp, right? You're not going to fly up into the air or down somewhere else into the crate. So that's why we're setting this equal to 0, and like I did in the portion up here in the x direction, I'm going to exchange the weight of the washer for the mass of the washer times g. And this way, I can move this whole quantity to the other side, and I have an expression for t cosine of gamma. So here's where the trick comes in, and I'm going to underline these two expressions in two different colors so we can kind of see what's going on here. Down here at the bottom, let's make a couple stars and indicate that we're going to make a calculation that we are going to come back to and reference later. And what we're doing is we're taking the left-hand side, t cosine of gamma, of this expression divided by the left-hand side of all this, which is t cosine gamma, or t sine gamma divided by t cosine gamma. If I said that incorrectly, excuse me. That means we can set the right-hand side of both of these expressions in this kind of format. So we're going to take everything here in red, put it in the numerator, take everything in blue here and put that in the denominator, and check it out. The mass of the washer divides out in the numerator and the denominator, so we end up getting the following expression, which still looks messy, but we've removed an unknown variable in doing so, and in fact, we get a double whammy for this process, because if you take t sine gamma divided by t cosine gamma, you eliminate t. And what do you end up with? Well, sine divided by cosine is tangent. So we did this neat little trick that allowed us to completely eliminate the tension in the wire and the mass of the washer to get this expression here equal to tangent of gamma. Now, this is not our answer. We still need the coefficient of kinetic friction between the ramp and the crate, but we're going to come back to this, hence the couple stars. So put it somewhere safe for now. Let's move on to the free body diagram of the crate next. We are thinking of the forces purely in terms of acting on the crate, which includes the total weight of everything inside the crate, which is, the crate itself, us, and the washer that's, attached to it. And then we also have the normal force of the ramp pushing back on the box as it slides down. And let's not forget, there's kinetic friction. There has to be, because we were we were explicitly told that we have to solve for it. So there's not a question of, why are we putting this in the problem. However, a good question to ask is maybe why is it pointing in the plus x direction? Well, if the net acceleration of the crate is in the negative x direction and it's moving down and to the left, we know that kinetic friction has to act in the direction opposite to the net motion. And so if the net motion is in the negative x direction, based on how we've set up the system, then the kinetic friction has to act in the plus x direction. So we do have some angles that we need to include here regarding the weight vector, and that's really easy. We saw that if we just include this little guideline here, we can say the ramp angle is right here, and hence it's also right here. That means we can break down our weight vector into the cosine and sine components, which act at right angles to one another, as indicated there. And also the crate is accelerating down the ramp in the negative x direction. So we can also include that off to the side. Speaking of moving things off to the side, let's do that to everything that we have here regarding our diagram and move on to the sum of forces on the crate. Hopefully, when we do F equals ma here, we can find something that will tell us about the coefficient of kinetic friction, because that's our goal. So, sum of forces in the x direction. We're looking for forces that either point up and to the right or down and to the left. So we have kinetic friction pointing exactly along the x-axis, so completely positive, no angle involved. And then down and to the left, we have our sine component of the total weight of the crate, hence that being negative. And since the whole crate, all the mass of the crate is moving in or accelerating down the ramp in the negative x direction, we have to put minus ma here, and I'll kind of write that like this. in the next line. As you can see, I've also exchanged the kinetic frictional force for mu sub kn. Now we're on fire. We have the variable that we're looking for, and we can start making a little bit of progress towards isolating that and solving the problem. The only issue is that we don't have an expression for the normal force yet. So let's jump into the other side, and we'll do the sum of forces in the y direction. And this tells us that we have the normal force acting in the plus y, and it's opposed in the opposite direction by the total weight cosine component. And as the crate is sliding down the ramp, it's not going up into the air and floating, or falling inside the ramp and like going through the center of the earth or something. So the acceleration in the y direction is 0 the entire time that it slides down along the crate in the x direction. And this makes things easy. You can just move this cosine component of the total weight. I think that's supposed to say W total, forgive me. And we can move it over to the other side, and now we have the normal force is equal to the total weight of the crate multiplied by the cosine of the ramp angle. And the idea is that I want to take this expression here, the W cosine theta, the total weight, pardon me, and plug it in right over here. And that's what this looks like at the top of the screen when we do that. And remember, we still have the acceleration being in the negative x direction because the crate and everything else inside of it is sliding down that ramp, and we've said down the ramp is negative. We are going to exchange the total weight of the crate for the mass of, or the total mass of the crate, pardon me, times g, which is reflected in this piece right here. So notice total mass, total mass, total mass. There's a total mass in each term on both sides. Let's get rid of it. Let's banish it and never deal with it again. It doesn't matter. We have now a way to very easily approach the coefficient of kinetic friction. I can take this g sine theta term, slap it to the other side, which will look like this, and then I can divide both sides by g cosine theta. And now I have the coefficient of kinetic friction is equal to this ugly stuff. And unfortunately, we still don't even know what the acceleration is in the x direction. So we're not done. We're still kind of stuck in a corner. Or are we? Here's a reminder. We were taking a look at this previous expression when we were investigating the washer. And we said, hey, it doesn't matter what any of this stuff is because it's equal to tangent of gamma. And we know what gamma is. That's just 22 degrees. And I can punch in tangent of 22 degrees on my calculator. That's what this number is. And you should get something roughly similar. And when we approximate it to the two significant figures to match the number of significant figures from everything else in the problem description, we'll get 0.40. And that is the coefficient of kinetic friction between the ramp and the crate. That is our answer. And it's very interesting to see that the frictional interaction between the crate and the ramp manifests as this kind of washer interior angle as the washer is hanging from the roof of the crate. And it all kind of ties into the idea that the crate and the washer, as well as us inside of it, we all share the same acceleration as we go down the ramp. And that about does it for this problem. Thanks for watching.